As we're talking about beams, we've been talking a lot about the bending stress and the moment. We've been doing a lot of things to calculate the bending moment for a beam. But as we did the shear and moment diagrams, moment isn't the only thing we care about, right? We also care about the shear. And the reason that we care about the shear is because if we were to break into a beam, right? Let's say we had a beam and it's subjected to some load. It has both the moment and the shear, and if we take a look inside of that, and let me take just a 3D cross section back of this beam. At some point that we cut through it, we're going to have that shear, right? We see that shear coming down through here. But we know from way back in the first couple of weeks of class, we learned that the shear stress happens on two surfaces, right? So the shear stress, back when we talked about shear stress, we had looked at that example where we said, oh, if I subject a book to shear stress, right? If I have some book and then I subject it to shear stress, it becomes this parallelogram. Right, I have it under that shear stress tau. I get a stress along two axes there, right? Like an equal and opposite reaction. So when I took this book and I said, all right, I've got a book here, and I subject it to shear stress, I get that like parallelogram shape, right? I get that angle. That's our shear strain. Our shear strain is that angle that it goes through in that parallelogram, but our shear stress was that stress subjected to it. And so not only was that shear stress happening along one side, but it is also happening on this other side, right? You'll sometimes see it labeled as like tau xy because it's happening in two axes. Right, so what that means for us when we start to think about this in a more 3D kind of way is that not only do we have the shear stress that's on this face where we cut through the beam, but that also means that if I were to kind of enhance this here, there is a shear stress going back through the beam. Let me draw this enhancement. I take a little square from the face here. Not only is there shear stress along this face, right? This is this shear stress along this face. There is an equal and opposite shear stress along that top face. So that's what we call transverse shear. That's the shear stress that's going through this beam in the longitudinal direction, right? So this is our longitudinal shear stress, and then our transverse shear stress is going back through the beam, right? So everywhere we have a shear stress on this face, there's our shear V, equal and opposite shear. I guess this is the same picture that I just drew. Equal and opposite shear where there's no shear on this front face. So this face experiences no shear whatsoever. It is through the beam, right? If we think about this as, let's say, X, Y, Z, maybe, then you're only seeing it on the Y face and the Z face, not on this X face. So that's this idea of transverse shear, that not only is there shear going down through the beam, down this direction, there's a shear, there is a transverse shear as well. This is our transverse shear. So why would we care, right? Why would I care if there's shear stress going through the beam, right? Well, it's because of the last couple of things that we talked about, right? We just talked about composite beams where we have, multiple materials glued together. So maybe, I took some wood and I glue it to a piece of metal, and now this is a composite beam, right? So the reason that I would care about this transverse stress is because this introduces a new point of failure, right? If I have a stress along this connection line, right where those two composites are glued together, that is now a source of weakness. It's a weak point for our beam, and our stress could be too high and our glue could fail. So we could have failures now, not only because of the bending moment, but because of this shear stress going through the beam. One other example that you might see similar to the book, when we subject this book to so imagine this is our beam, and I subject it to this force, and I'll kind of bend it up. I subject it to force P. When I bend it up, you can see that this side that's bonded together, remains straight. But this side, where the leaves of the pages are kind of loose, you can see that they all kind of move up against each other. They slide against each other, whereas the other side, they don't have that option. They have to be bonded together. Here they slide up against each other. So if I had a bunch of boards sitting on top of each other, or pieces of paper, or whatever they are, sitting on top of each other, and I subject them to that force P, what they would do is they would curve up and slide against each other. Right? So there wouldn't actually be any shear stress here. They would just be sliding against each other. But if they're glued together, right? So now I have these three boards glued together. All of their ends have to remain in the same location. Right? All of these ends are bonded. They're all glued together. So now there's stress at the glue between each of those beams. And even if it's not a composite, there's still stress within the beam itself. Right? Within that beam itself, let's say we have just a square-ended beam like this. The shear stress is not one constant value. Before, we used to talk about this as, okay, let's take the average shear stress as the shear over the cross-sectional area. So we said, all right, there's a shear through here, and then this is our cross-sectional area, right? When in actuality, it's not constant through the cross-section. It works a lot like our torsion, where we had no shear stress at the outside, and then as you got closer and closer into the center for something under torsion, that did have shear stress, right? That's our maximum shear stress as we got to the center. So that's exactly how shear stress works in beams. It's not constant all through the beam. Instead, our shear stress is really small, and then it gets bigger shear, and then smaller and smaller. So that at the centroid, this is where shear is a maximum, is at the centroid, or Vmax at centroid. And then there is no shear at the very top and very bottom, the outermost edges of the beam. Shear is 0, and then shear increases till we get to the center, and then it decreases again. So we're going to see the most shear stress at the center of our cross sections, wherever those centroids are. That's where we see the most shear. So what we're going to be able to do now is actually calculate the location where we have the most shear, right? Where the shear is greatest, where the shear force is greatest, so that we can find where the shear stress is greatest to make sure that it's not going to fail. So let's look a little closer at that idea, right? This idea that shear stress is not constant across a cross-section. So if I take, say, this I-beam, for example, we'll pretend like that's an I-beam that's drawn good and connected. If I were to look at the shear across this cross-section, the shear stress for this cross-section, what I would see is that I have a little bit of shear stress. So my shear stress, let me kind of plot it if it were a graph, where this is 0 and then outwards represents our shear stress. We kind of start at 0 and then we have more and more shear stress, right? We have more and more shear stress, and then we get this abrupt change in cross-section. We're going from this really fat to this really skinny portion of the cross-section. So what that means is that our shear stress is actually going to jump up. We're going to see a huge increase in our shear stress right where that cross-section changes. And now we've got a high shear stress till we hit the centroid, right? So our center of our beam is somewhere in there. High, and then it comes back down. It gets lower and lower till we hit that cross-section change again. Shoots back down, and then there's just a little bit until we get back to zero shear stress. So this would be kind of a representation of what's going on and why we might not want to use the average shear stress equation for this full cross-sectional area. Because if we use the average, we're going to get something maybe about here, right? So for this, we don't want something that's going to be off by multiple magnitudes, right? Say we have a maximum of 25 megapascals, but when I calculate this, I only get 5 megapascals for the average shear stress. We would be pretty significantly under designing this thing if our shear stress, if our max shear stress for the beam is actually 5 times greater than the average. So that's why we would want to look for the exact shear stress. And the way we do that for our beams is if we've got some beam here and I take a look at the cross section, right? So I want to let me take just this little dx for the cross section, and it'll just be some shape. So for this shape, what I care about is I care about where the centroid is, and then I'm going to pull a few things related to that. So my equation for this, let's write our equation, kind of break down what that means. Our equation for this, for the exact shear stress, is going to be shear stress, tau, is V times Q over I times T. So V is our shear stress. V is just the shear force. Sorry, V is the sheer force going through the beam at that point. Right, so that's our V. That's our shear. Q is the first moment of area. The first moment of area. And we're going to talk about him a little more in depth. We'll do an example problem of how you calculate this Q value because he's new. But essentially it's the top half of our centroid equation. So it is y tilde times a. So if I look at my cross section here, I've got the V going through it. My Q is going to be, let's say this is the centroid, which we'll label NA for neutral axis. NA is our neutral axis, also known as the centroid. So you might see that written either way in some of these problems, but neutral axis is just your centroid. So our Q is calculated for whatever our point of interest is. It's going to be the area times the centroid of that area of interest. So let's say that I wanted to find the shear stress at this exact point. Call it point P. At this exact point. Then my area is going to be this line, this cutoff line right at P, the entire area above that point of interest. A. And then we would get our centroid of this area, right? So the centroid of this area, maybe it's about right here. It would be the distance from our centroid of this area to the neutral axis. That would be our y tilde. And this is how we would pull our Q value. So it's the area above the point of interest times the centroid distance away. And it could be above or below the neutral axis, but you're doing whichever one is farther out from the neutral axis. So if our point were down here, let's say this is our point, then our area of interest would be this area down here. So it's always the area away from our neutral axis, where the greatest value of Q that we could have would actually be at the neutral axis. So there are going to be a lot of times where we're going to want to find what the centroid is. We're going to find the shear stress at the centroid because that's where Q is maximum and that's where our shear stress is maximum. I'm going to make a little note on that. Note that shear stress is max and Q is max at neutral axis or at the centroid. All right, so we have our shear force times Q, this y tilde times A, over I, which is our moment of inertia. We've seen that guy a lot by now. He came up a lot in our bending moment equations. So that's our standard moment of inertia for this whole area. So it's the moment of inertia for the entire shape, not just the shaded region, but the entire shape. So for entire cross-section. So it's not going to change. Our Q value can change, but our moment of inertia is the same for whatever that cross-section is. No matter where we take it on this beam, assuming this cross-section is constant, moment of inertia is going to be the same. And then finally, our last term in here is T. And T is the thickness at the point of interest. So the thickness of our cross-section at the point of interest. For this example that we have here, that would be this distance right here. This distance would be T. The thickness from one end to the other at the point of interest. So there's a lot going on in this equation. There's a lot of new things. Let's go ahead and do an example talking a little more in depth about this new Q term, this first moment of area. First moment of area. And then we'll look a little more in depth on how we use this exact shear stress equation so that we can calculate our maximum shear stresses to make sure that our beam is not going to fail, right? We're also going to be able to use this to do things like design the cross-section and design fasteners, right? So if we want to glue it or use nails or bolts or things like that, we're going to be able to use this equation to do a little bit more detailed design. So again, to kind of sum all of this up, there's a shear stress on the surface of the cross-sectional area when we make that cut, and it is the same, it's equal and opposite through the beam. So when we find the exact shear stress at this cross-section here, it's the same one that's going back through the beam being transferred to any glue or bolts or nails that may be through that cross-section. Let's talk a little bit more in depth about this Q term, right? This is a new property of the cross-section that we haven't seen before. So again, this is Q. Q is also called the first moment of area, but most of the time you'll just see it as Q, or you'll see it written out in its formula form, which you'll see as the centroid times area, right? So that's what Q is. Q is our centroid times our area. And sometimes you'll see it with like this y tilde a or y bar a, or sometimes you'll even see it with this like y tilde prime and a prime. And all this is doing is letting you know that it's not the full cross-sectional area that you're looking at. It's not the centroid of the entire cross-section. If you have your cross-section here, there's my little loaf of bread, I take a cross-section. My Q is only the area that we're in, from the point that we're interested in. So if we're interested in, say, this point here, then I want all of the area above this point. So this is where I'm getting my Q value. This is my neutral axis, or my centroid for the overall shape. And then I need to find my centroid. Here, this little crosshairs for the little centroid, little center of this shape is maybe somewhere in there. So it's this y tilde distance from the neutral axis, right? Not from the bottom, not from it, just measured from the central axis to the centroid of the shape. And then the area is the area of this shape. So it matters where you're taking this cue from. The point of interest is really, really important. The other thing to note is that much like moment of inertia, it's a property, it's a geometry property, right? It's a property of the cross-sectional area. And so we get units that don't always make a lot of sense, right? If we look at this, we're multiplying a distance times an area. And so our units that we typically get for Q are going to be things like meters cubed or, millimeters cubed, inches cubed, feet cubed, so on and so forth. But these are not measurements of volume. It's just a representation of the geometry, just like moment of inertia, even though it has units of, inches to the fourth or millimeters to the fourth, it's not actually in the fourth dimension. It's just a property of the geometry. It's just something that we use to get the values that we actually are interested in. It gives us a property value and we say, okay, this represents this geometry. I can use this representation to get something that's actually tangible, something that actually makes sense as a real world answer, even though Q as its own term doesn't really have any real world value, doesn't really mean anything. We need to put it into other things to give it meaning. But it's going to get plugged into our shear stress equation, right? So for us, this is where we care about it. Shear times Q over moment of inertia times the thickness. Again, that thickness is this width right here. So this length would be T, and then V is the shear stress, or V is the shear force. V is the sheer force on this cross-sectional area. So let's go ahead and look at a quick example of how you calculate this Q before we go into our big shear stress examples. All right, so here I've got a cross section, it's a cross section. Anyways, it's a section that's shaped like a cross for our beam here. And it's got 100 millimeter sections all along it. And then we want to find Q for these two different case scenarios. So we want to find Q at A, and we also want to find Q at B. These are going to be two different Q values. So the very first thing we need to do is we need to find where the centroid is. Now, thankfully, this shape, it's really easy to tell where the centroid is. We don't actually have to go through the full centroid equation because it's perfectly symmetrical on top and bottom. So we know that the centroid is going to fall exactly halfway through the shape. So my centroid falls perfectly through the 150 millimeter mark here, right? 100, 100, 100. So it falls here, 50 millimeters on each side of that 100. Which is exactly where our point A falls. Our point A falls right on the neutral axis. So what this tells us is that this is going to be the maximum value of Q. Again, the max value of Q that you can have, right? Q max is at centroidal axis, on the neutral axis. This is also where your max shear stress is. Max shear stress is at neutral axis or centroidal axis. So since A is falling right on the neutral axis there, right on the centroidal axis, we're going to have Q max. This is the highest Q value we can have for this particular cross section. So the way that we want to go about this, is I think it's easiest to draw yourself a picture. Draw the cross-section again with only that area that you're interested in, only that area above the neutral axis that you're interested in. So for A here, I wanted to redraw this. I'd say, all right, here's my neutral axis. And then here is the portion of the cross-section above that. So I have that 100 millimeter and the 50 millimeter portions of the cross-section. I'll go ahead and add these distances, 100 millimeters for each section across here. And I'm looking for this entire area. This is our area of interest. It's the area above point A. So my Q at A is going to be, again, it's the top half of that centroid equation. Y tilde A. And again, we can use this just like a centroid. We can do an integral to find each of these. We can separate them into different shapes using composite bodies method to find the centroids, which is actually the easiest way to do this, right? I can just find the centroid of my bottom shape, right? If I split it like this, I can find the centroid and area of the bottom shape, add it to the centroid and area of my top shape, and that'll give me my total Q value. If I go ahead and do that, the centroid for this bottom shape here is going to hit right in the middle, right? So it's this 25 millimeters from the neutral axis, right? So that would be Y tilde 1, it would be 25 millimeters. My centroid up here would be, the center for just the top portion would be 50 millimeters, but I need to add that 50 that's below it, right? Distance from the neutral axis. So this distance would be 50 plus 50 is 100. That would be Y tilde 2. And then I just need the areas for each of those. So my area for this first one, area would be 50. It's 50 millimeters tall times 100 plus 100 plus 100 is 300. So that gives me something. I'm going to go ahead and put it in my equation down here, I think. So it'll be the 25 millimeters, it's Y tilde 1, times the area of the first shape. So 50 times 300. Right, that's just for this bottom shape here. And then for the top shape, my area, my Y tilde we said was 100 millimeters. And the area is 100 by 100, right? A 100 by 100 square. So all I need to do is add all of those together. I punch all of that into my calculator, and I get 1375000 millimeters cubed, since all of my answers were in millimeters. So you could have gone ahead and found the centroid for this shape, and then gone and calculated your Y bar from that. You can pull it right off of the image too. So it's up to you if you wanted to find the centroid for the whole shape first, and then just use one single Y bar times A, or if you want to do this kind of this composite method, right? Just adding the two together. So that would be A, right? That would be our Q value if we were interested in the shear stress at point A. But what about our shear stress at point B here? Point B is right at this transition where we're going from the wider portion of the cross to just the upper portion of the cross. So if I wanted to draw that one, let's go ahead. I'm going to remove this and draw a fresh picture in here. I'm going to start with my neutral axis. I'm going to draw in the top half of the cross again. But notice this time, I only want the portion above B. So that portion above B is just this section here. This 100 by 100 portion top of the cross. Right, 100 by 100. But why did I draw in the stuff below it to the neutral axis, right? So when I want this y tilde times a, that y tilde is the distance to the neutral axis. So my centroid, right in here, I know is 50 up from the cross, but the y bar is measured to the neutral axis. This distance is 50, so it's going to be 50 plus 50 is 100, is my y tilde for this shape. Right, centroid of the shape to the neutral axis. That's our y tilde. Whoops, not A. So if I want my Q for B, all right, QB this time, BBB, y tilde times A, my y tilde is the distance from the neutral axis to the centroid of the portion I'm interested in. So that's 100 millimeters. And then it's the area. And again, it's only the area that I'm interested in. It's not this full cross-sectional area, just the area I'm interested in. So it's the 100 by 100 square. Right, this is just the area I'm interested in, the area above point B. And that, when I punch that into my calculator, I get a very nice 1 million millimeters cubed. So that's how we go about calculating Q. And remember, it's not always the area that is directly on top. It can be either the area above or below. It's just the area that's farther away from the neutral axis. So just as a bonus example, if I wanted to find, let's say I have a point C here. Point C, and it's 50 millimeters from the bottom. And I wanted to find the Q value for that one. Well, my Q value, right, my area that I'm interested in is the area away from the neutral axis. So this would be the area I'm interested in looking at. So my centroid, still measured from the neutral axis down, my centroid of this shape is going to be 25 millimeters from C, and then I know that this distance is 50 millimeters, and this distance is 50 millimeters, so that gives me a total y tilde of 50 plus 50 plus 25, 125 millimeters, and then my area would just be this area in red down here. So area would be 50 times 100 millimeters. And then I just multiply these two together to get my Q. So my Q for C, hypothetically, would be 125 times 50 times 100, which I think I plugged that into my calculator, and that gave me QC is 625,000 millimeters cubed. Right, so we also noticed that our Q values got smaller and smaller the further we moved away from our centroidal axis. The further you go from the neutral axis, the smaller and smaller Q gets until you have 0, right? There's no area once you hit the very top edge here, right? No area means that you're not getting any Q value. No Q value means that you're not getting any shear stress. So your shear stress is also 0 on these very top edges, on this top outer surface. So we're going to use this Q value every time we're calculating this exact shear stress. So let's go ahead and take a look at some examples of how we use that. Now that we can find Q, let's use this shear stress equation and see how we calculate the exact shear stress. This example asks us to find the max shear stress in the beam and also determine what the shear stress is at the flange web joint. So the flange is the thicker part, right? It's the top and bottom parts of our I-beam, and the web would be the thinner portion that's connecting those two, so the portion in the middle. So essentially they're asking us to find the max shear stress and then find the shear stress right here, right at this point where the flange and the web are welded together. We want to find it here, and we also want to find the max shear stress. So again, the max shear stress always occurs at the neutral axis, occurs at the centroid. So looking at what we're given here with this little I-beam type of cross-section, we have 20 millimeters, then 200 millimeters, and 20 millimeters. So this is a perfectly symmetrical I-beam. So what that tells us, since this is perfectly symmetrical, top and bottom, we can go through and calculate a centroid, or we know that the centroid is going to happen exactly halfway through this beam. Right, so 120 above and 120 below. 120 millimeters. So this is the axis that we're looking at, the neutral axis here, to calculate our max shear stress. So that's the one that we're going to calculate first. Let's go ahead and look at what we need. So our equation, shear stress, for an exact shear stress, right, our max shear stress, V times Q over I times T. So we're looking at our I-beam here. Our V is given to us. It says here V that the shear force is 80 kilonewtons. So boom, already got one thing checked off the list. Our shear V is 80,000 newtons, right? Just doing that quick conversion from kilonewtons. Q and I are both properties of the geometry. We'll come back to those in just a second because we can already write down what T is. T is the width, right? The thickness at the point that we're interested in. So T would be our thickness right here. This portion right here is 15 millimeters wide, 0.015 meters. So now let's go ahead and take a look at our geometry properties. Let's do our moment of inertia calculation, our I calculation first, because we're going to use that for both shear stresses that we're calculating, right? The moment of inertia doesn't change regardless of where you're taking the point. You're always doing the moment of inertia for the entire cross section. Remember, it's I for the entire cross section, which is our, you recall from statics, it's that IX plus AD squared. For this, since we're working with this kind of composite body shape and they're all rectangles, you'll sometimes see me rewrite this as the sum of 1/12 base height cubed plus AD squared. And some people like to do this in a table kind of format where you go through and calculate the area, calculate AD squared, calculate the moments of inertia for every shape, and put them all in a nice table so you can add everything together. That's usually the way that I like to do it too. I'm a really big fan of table form. But for this one, I'm going to go ahead and just plug them into the equation. So for my moment of inertia, I have this top area, right? That's this 20 times 300 millimeters. That's the area that I'm looking at. And it's the same on the top and the bottom. And they're the same distance away from my neutral axis, same distance away from my centroid. So I can actually just multiply whatever value I get for one of them times 2, since I have 2 of these rectangles. Right? These 2 rectangles are the same. And then this center rectangle is the one who's going to be different. So my first rectangle, right, I'm gonna have 2 of these for the top and the bottom, and then I'll just calculate all at once. 1/12 times the base of the rectangle is 300 millimeters. I think I'm going to go ahead and convert these to meters. Instead of leaving them all in millimeters, I think it'll just be easier that way. It's up to you. It should work out the same either way. But I'm going to go ahead and convert all my units now. So instead of 300 millimeters, I'm going to use 0.3 meters. That's my base. And then my height is 20 millimeters. So 0.02 cubed. And then I need to do AD squared. So A area for the rectangles is 0.3 times 0.02. And then D squared. Again, that D term is the distance from the centroid to the centroid of the shape, right? It's a y tilde value. So the distance from our neutral axis to the centroid of this shape, centroid of this shape happens halfway between the 20 millimeters, so 10 millimeters. So that would be 110 millimeters, right? Adding this 100 distance here. Distance away from the centroidal axis is 110 millimeters squared, or 0.11 meters squared. So that takes care of the moment of inertia for the top two squares, but I don't want to forget this middle portion. So my middle portion plus 1/12 base. Here the base is 15 millimeters or 0.015 meters. And then my height is the full height of 200. So 0.2 cubed. And then notice, since my centroid of this rectangle and the centroid of the overall shape is the same, the D is actually 0. There's no D term since the centroids overlap. They have the same centroid. There's no distance between the centroids. So there's actually no added term on here. But this would be our full moment of inertia that we would just punch into our calculator. So if I put this whole big thing into the calculator, I get a moment of inertia of 1.556 times 10 to the negative 8th meters to the 4th. So that only leaves me with one more thing I have to calculate, and it's that pesky new Q value, right? I've got the V, I've got the T, I've got the I just need Q. So for the max shear stress, again, Q is that area from the neutral axis. So I'm going to go ahead and redraw this little cross section over here just to be the portion I'm interested in for Q. So let's redraw. Let me leave him kind of on here so I can see him. This is for Q. So for Q, I have this T shape now, right? Because I have the neutral axis here, right? Our centroidal axis. My distances, let's see, we have 100 millimeters, 20 millimeters. This full one is 300, and then this middle one in here is 15. And for this guy, I'm interested in everything for this Q. So when I go to calculate Q, this is Q max, right? Q from the centroidal axis. Y tilde times A. So my centroid for this lower rectangle is going to happen 50 millimeters away from the neutral axis, right? It's 100 long, so it happens 50 millimeters away. Halfway through that rectangle is going to be our first Y tilde, right? That's our first distance away, and then the area is going to be the area of this smaller rectangle, 100 times 15. And then if I go ahead and look at my other rectangle, right, my top rectangle, my centroid here is going to happen 10 millimeters in, but I need to add everything that's below that as well. So y tilde for the second rectangle is 110. And then the area is going to be 300 times the height of 20. Now again, I did convert all of these before, so I think I'm going to go ahead and convert them all again. But I've got all my values written in green and purple here. I can just plug them into my equation and convert as I go. So my Q max is going to be those two separate centroid top half of equations added together. So it's the y tilde, so that's 0.05 times the area of that lower rectangle. Whoops, sorry, I already did the thing I said I wasn't going to do, and I need to put that into meters. All right, 0.1, not 100, right? 0.1, and then it was times 15 millimeters, so 0.015, plus our second one, our purple rectangle on top, is y tilde is 0.11, and then the area is 0.3 times 0.02. That's our full Q equation. So I punch that into the calculator and I get a Q max of, let's see, what did I get? I got let's do this in scientific notation. 7.35 times 10 to the negative fourth meters cubed. So that's all I need now. Those were all of the things that I needed, the four terms that I needed to find this shear stress. VTIQ. So let's go ahead and plug those in. Right, that's just our very last step. Our shear stress is going to be our shear, we said was 80,000 newtons, times Q, just found our Q, 7.35 times 10 to the negative fourth meters cubed, all over I, our moment of inertia, 1.556 times 10 to the negative eighth meters to the fourth. And then finally that thickness, again, the thickness there at the neutral axis is 15 millimeters. That's 0.015 meters. And I converted all my units as I went because I know that I wanted everything to be in the standard unit. If I put everything into newtons and meters, then I know that this is going to work out to be newtons per meter squared, right? It's okay if you have them all in millimeters. Just know that your answer is going to work out to newtons per millimeter squared, which is fine. That's totally acceptable. A newton per millimeter squared is a megapascal anyways, so it could be helpful to save a conversion. Anyway, so I do plug this into my calculator, and I get 25, 200. See, I get a huge number anyway, where it'd be much easier to just have this in megapascals. 25.2 megapascals. That is our highest shear stress for this I-beam. And that could be really helpful to know if, say, for example, our metal can't handle that. Say we have aluminum that has a max shear stress of 25 megapascals. Maybe that this is too high, and our I-beam is going to start shearing from itself, right? It can't handle that level of shear. It's going to start tearing like aluminum foil. So this is exactly why we would want to calculate shear stress, so that we can prevent failure. But that's our max shear stress. Let's go ahead and take a look at our other portion here, the shear stress at the joint. Again, at the joint is this portion right here. So this portion right here at the joint, we can use the same shear, we can use the same thickness, right? We want to use the smaller thickness here because that gives us a higher value of shear stress. So we'll still use that same thickness of 0.015 and the same moment of inertia, right? We did that. That's just a property of the full cross section, so we don't need to calculate that again. But our Q value is going to be different, right? That's our major change here for that shear stress. Instead of doing this whole top half of this T, what we're going to be doing is only this upper rectangular portion. So in this case, right at that joint, here's our the top half of our cross section, the neutral axis. We're only looking at this portion to find our Q. So Q is y tilde times A for just this upper portion. We said this distance was 100, this one is 20. So the centroid of this shape is going to happen halfway through the rectangle, 10 millimeters, and then we add the 100 to that. So y tilde is 110 millimeters. And then the area is just that 300. This length is 300 times 20. In this case, Q is going to be 110 millimeters times 300 times 20. Or convert to meters, right? So if I go ahead and multiply that out, convert it to meters, I get a Q at the joint of 6.6 times 10 to the negative fourth meters cubed, right? So a little bit smaller than the Q max value that we found over here. But it does mean that all we need to do is we just need to erase this Q value that we found for the max shear stress. And we can go ahead and put in that new value we found, 6.6 times 10 to the fourth. Same thickness, same I, same V. So the only thing that changes is that instead of it being our max, this is the shear stress at the joint. And I plug this into my calculator, just with the 6.6 instead of that 7.35, and I get 22.6 megapascals. Again, very useful to know if, maybe at that joint, the welding can't handle that much stress. Maybe we fail at the welds there. Or let's say we wanted to use a different type of fastener, like glue or nails or bolts, and we wanted to change out, while we're still in the designing process, we want to change out what kind of attachment it is to attach the top portion of this steel to the webbing of this steel. Then we would need to know what kind of shear stress it needs to be able to handle so that we can design for that, right? So that's our purpose in doing these shear stress calculations. Let's take a look at another example. In this one, we have a beam that's made of two boards that are glued together here at the T. This is the cross section here. It's a little T shape glued together here, two distinct separate boards. And we want to determine the shear stress in that glue necessary to hold the boards together, right? So we want to know the shear stress so that we can know if the glue can hold the boards together at the point where they're joined. So at this little white dot here, we want to find the shear stress. So I want you to go ahead and try this one out for yourself, right? See how many of these components of our shear stress is shear force times Q over I times T. How many of these components can you work through and get on your own? And then we'll look at this together. If you need a hint, I will say this beam over here is how you have to get your shear. And it goes back to where we first talked about beams with a shear and moment diagram. So go ahead and give that a try and see if you can get the shear stress, or at least some of the components to get the shear stress. So let's go ahead and break down how we get each of these components for our shear stress equation. I'm going to start with maybe the most difficult one, maybe it's the easiest one for you, this shear, right? This V. How do we get this V? We're given this loading diagram, and we know that from this beam, we can go ahead and get a shear and moment diagram so that we can find the shear, right? We want to find the max shear stress in the beam at the joint. So we want to look for the highest shear stress, or the highest shear in the beam, right? We're looking for the highest shear value. So if I go ahead and, well, before I make this shear diagram, I do need to solve for my reactions, right? So all I have is this 6.5 kilonewtons per meter distributed load halfway along the board here, or the beam here. So I have a reaction force at the pinned end and a reaction force at the roller end. So I'll need to find each of these, and I'll do that just using my statics, right? I can take a moment. Let's take a moment about the roller. If I take a moment about the roller, then I can find this value here. I'll go ahead and call this B, call this A. So a moment about A. I'll get, let's see, my negative 6.5 kilonewtons per meter. It's over 4 meters, and its resultant is right here, right? So this would be our 6.5 times 4, and this distance is 6 meters, right? It happens halfway through our rectangular distributed load. So 4 plus 2 is 6 times 6, and then plus B times its distance away is 8. So that gives us a B reaction value. When we plug that in the calculator, 6.5 kilonewtons. And then from our sum of Y forces, we can find that our negative 6.5 times 4 plus the B value, 6.5, plus the A value gives us our A reaction is 19.5 kilonewtons. So now that we have those, it'll be a lot easier to make the shear diagram, right? So our shear diagram here, we have A at the very left end, so that pops up our shear diagram by 19.5, or by, I have these backwards, I'm so sorry. I have these written backwards. This is 19.5. This is 6.5. My mistake, sorry. This is 19.5. This is 6.5. Okay, there we go. Much better. So this pops up, A is 19.5. B, I still wrote them backwards. What's wrong with me? Oh my goodness. We would expect the right side to take on a lot more. It's closer to the load. All right, A is 6.5. B is 19.5. Sorry, that is correct now. Okay. Everybody makes mistakes. That's why I don't dock a lot of points for these. Anyways. So we're going up on our shear diagram by 6.5, right? Because of this 6.5 force pushing our shear up. And then there's no loading for this 4 meters, right? So we go 4 meters straight across, 6.5, and then we go down 6.5 kilonewtons per meter for 4 meters. So for my first meter, I go down by 6.5. That takes me to 0. Then I go down by 6.5 for the second meter, the third meter, the fourth meter, to the end. So So that takes me down 6.5 times 4 to a negative 19.5. So that's my shear diagram. And what this does is this gives me my max shear value, right? This gives me what the highest shear this beam is experiencing. The highest value of shear that this beam is experiencing is at that end B there. At the very end, this is the highest value of shear that we're seeing. Even though it's negative, it's still the largest value. So that tells us that our V for our equation is 19.5 kilonewtons. So that takes care of 1. And that might be the easiest portion of this, but if it's not, it's definitely T. T is our thickness of our joint that we're looking at, and we're looking at this white dot here. Right? So that's the point of interest. The thickness there at our point of interest is going to be the thickness of this skinny portion of the T. So that's 30 millimeters. So we've knocked out 2 of them. Now we just have to get Q and I. And remember, our moment of inertia is for our entire cross-section, this entire T. And our Q is just for that portion above the point of interest. So to do either of these, the secret to finding these is that we have to find a centroid first. Right? So we're not given a centroid for this T shape, and it's not symmetrical. It's not vertically symmetrical, right? It has a larger top and a skinnier bottom. So we can't just say that it happens at the halfway point, because it doesn't, right? That's not where the centroid is. We're going to have to use our centroid equation to find where the center of this T is. I'm going to find my centroid first before we do anything else. Our centroid is sum of y tilde A over sum of areas. So our y tilde A, I'm just going to measure from the very bottom. If I look at my bottom shape, draw them out here. Here's our bottom shape, or here's our top shape. Here's our bottom shape. Let me draw them on top of each other. Just draw them again over here. All right, so our y tilde A for our bottom shape is going to be the centroid of this rectangle. So the center through a 150 high rectangle is halfway up. This is 75 millimeters. And then our area would be the 150 times 30. So I have 75 millimeters times 150 times 30. Plus the centroid of my top portion. So this guy is 30, so half of 30 is 15. And then I need to add everything below him. So that would be 150. So 15 plus 150 is 165. 165, and then times the area of the top rectangle is 15 times 150, oh, not 15, sorry, 30 times 150. 150 times 30, right? 150 long, 30 tall. 30, 150, 165 is our y tilde. And then our areas, they both have the same area, but we still have to add them together. So 150 times 30 for the bottom rectangle, and 30 times 150 for the top rectangle. Right, same, just base times height. So I'm going to go ahead and plug all of that into my calculator, and that gives me a centroid of 120 millimeters. 120. So that's hitting about right here. Y bar, our neutral axis, is at 120 millimeters. Right? And you'll notice that's not perfectly halfway between the bar, right? It's what this is 180 total. So halfway would be 90, but this is more like 2/3 of the way, right? 120 millimeters up on this T-shaped cross section. So now that we have that, we can go ahead and calculate either Q or I. I think I'm going to do Q first because we already did this Y tilde A stuff. So we might as well go ahead and look at what Q is. So our Q, if you remember, is just that portion above the point of interest. And our point of interest is right here, right where those two boards join. Our neutral axis is 120 millimeters up. So that would make this distance, let's see, this is 150 tall, so 150 minus 120, this is 30 millimeters. And then they gave us the top of this T is also 30 millimeters. And then this is 150 by 30. And so to find this Q, I'm looking at just this area above the point of interest. Just this area here. So Q is Y tilde times A. My centroid for this shaded area, gonna be right in the middle here, halfway through this 30, so here's 15. And then this distance here we said was 30, so 15 plus 30 is 45. 45 millimeters times that top area, 150 times 30. Gives me a Q value of 20.2500 millimeters cubed. And this time I think I'm just going to keep everything in millimeters because a Newton per millimeter squared gives me megapascals. So I'm hoping that I can work it out to just be megapascals. Newton per millimeter squared equals a megapascal. All right, so I've got Q. Oh, that's actually exactly where I did not want to put that. Move that handy conversion up there, I guess. And I can add Q to my collection of variables that I know. 20.2500 millimeters cubed. And then finally, I need I. I need moment of inertia. And again, for the entire cross-sectional area. Moment of inertia. So, whoops, that's not the color I want. Let's do this in, I don't know, blue, I guess. I is our I plus AD squared. Right, for that whole area, it's two rectangles, so I know it's going to be the sum of 1/12 base times height cubed plus area times distance from centroid squared. So we're going to do that for each of the two rectangles, which I will put back down here for reference. They were 150 by 30, 150, 30, 30, 150. And we'll go ahead and do those. We'll just do this summation right down here. So 1/12, and then my bottom rectangle. Base is 30, height is 150, plus the area is 30 times 150. Oh, sorry, 150 cubed, my bad. 12 times 30 times 150 cubed, plus the area, 30 times 150, times the distance from the centroid of this shape to the centroid of the overall shape. So again, that centroid is coming through at 120. And the centroid of this lower rectangle is going to hit at 75. Right, half of 150 is 75, so this is going to be 120 minus 75. That's the distance, this distance here from the centroid of the overall shape to the centroid of just the rectangle squared. So that's the moment of inertia for the lower rectangle. Now we'll go ahead and add on the moment of inertia for this top rectangle. So 1/12 base is 150 times height, 30, cubed, very important, cubed, plus the area, 150 times 30, times the centroid distance, the centroid distance difference. So here my centroid is hitting at 15 plus 150. We said this hits at 165. So 165 minus 120, right, to get this distance here. 165 minus 120 squared. And then I'm just going to punch all of that into my calculator so that I can get my moment of inertia. Again, I left everything in its millimeter form, so the answer I'm going to get is going to be in millimeters to the fourth. Millimeters to the fourth. So I get 2.7 times 10 to the seventh millimeters to the fourth. Whew, all right. We found all of the ingredients. Really, the hard part is knowing what your Q needs to be, and then actually going through and brute forcing yourself through all of this math. Right? There's a lot of steps. There's a lot of little places where it's really easy to mess up. But once you have these 4 things, you should be good to go. You can just plug each portion right into our equation. So let's do that. I'm going to move this. Don't need these reactions. Get them out of here. Delete. And we'll do this. Height. Shear stress is V 19500 newtons times Q 20.2500 millimeters cubed over our moment of inertia, 2.7 times 10 to the seventh millimeters to the fourth, times the thickness there was 30 millimeters. So I get a shear stress with this all worked out in newtons per millimeter squared. So when I plug that into the calculator, it gives me 4.875 newtons per millimeter squared, or as we just said at the beginning here, Newton per millimeter squared is a megapascal. 4.875 megapascals. And that's it. That's all of our steps. Really, it's knowing how you can find shear. We can find shear in a few ways. A shear and moment diagram is a super common way that we find the max shear. Knowing how to find Q, this Q, understanding what centroid, what area you're looking at. And then, of course, just being able to calculate this moment of inertia. There's a lot of little pieces. It's easy to get tripped up, easy to make a miscalculation that follows through the entire problem. So just be careful of the numbers that you're plugging in. Be careful of your reactions. Had I flipped these two, I think actually had I flipped the 19.5 and the 6.5, we still would have worked out to have the same maximum. But that may not always be the case. So there's a lot of little things that can trip you up. But we do, once we get there, once we get all of these 4 values, it's just a matter of plugging them in and spitting out the answer for shear stress.